or any kind of resectorization was done after the FRA implementation. I don't know that. But I would say that actually the workload values, as I mentioned, this is post-ops analysis. So we have used only flown trajectories for our calculations. So the workload formula which is used is actually, if I remember well, using only 3 possible tasks which are somehow weighted, and probably this is influencing the results of the obtained workload. So I'm not so sure whether I was answering the question, but this is actually the problem with this analysis, because it is post-ops analysis. I mean, so we cannot say how the people were doing the operation and how the air traffic controllers were working, etc., because we don't have those kind of data, and we couldn't perform such a kind of analysis.
Now, in principle, you can of course find out, go to the sectors and find out if they made change.
Yeah.
The real problem, of course, is that in post-op analysis, you have no control over all the parameters. You are a victim of what they do. That's why
yes.
When you go to your own simulations,
yeah.
then you have these parameters under control, and you can look at sensitivities. And that is the limitation of an operation. And you cannot play with parameters. Yeah? You cannot study sensitivities.
Yes, yes, I fully.
But it's very clear.
Yeah.
The kind of work you do is absolutely very valuable to get insight in these kind of effects.
Yeah, thank you, thank you.
Then there is a question by Milan, and I think Milan already knows the answer. He asked, based on this, would you recommend free route airspace strongly or not?
Yeah, it's a political question. Yeah, yeah, I would definitely recommend free route airspace, because there are many different benefits from it. Definitely from the airline point of view, let's say the shorter routes and etc., less fuel burnt. Of course, there is environmental issues which are positive, etc. So I would recommend free route airspace, definitely.
Okay, I'm a bit surprised that you are so convincingly. I thought in the question of Milan, there was more, it's a balance, and it's very difficult for a researcher to, you pictured it well in your final slide.
Okay.
But for a researcher, very difficult to make decision.
No, I wouldn't. Yes, I'm definitely only researcher. I'm not a politician or somebody who is deciding about it. But I would say that in different areas of the European airspace, free route airspace is used in different ways. For example, I know in Serbia and Montenegro here, and as well in Croatia and Slovenia, we have this common airspace in which free route airspace is actually applied 24 hours for, I think, more than a year and a half or something. So it has a positive effects. Okay, from one side it's positive, from other side couldn't be or shouldn't be positive. I know, for example, that in some areas in Croatia, for example, and I have a friend there who was talking that actually the implementation or way how it is implemented, it was not good from the workload point of view. So the air traffic controller in operations are suffering a lot because of this, because they couldn't know where they could expect potential losses of separation, for example. Previously, they were used to it, to expect them in certain points in which you have a crossroads between the airways, etc. So there is a plenty of, I would say, plenty of issues which should be further on investigated. And this is something in which probably we will go in our future. Maybe we will add some other parameters, not only workload complexity and safety, but maybe environmental and other ones. But it seems to me that free route airspace has, or it could have, let's say, a positive effects. Maybe the choice of the MUAC airspace, which is, let's say, the densely populated, let's say, in the Europe, it's not a real one that you can, based on those results, to say yes, should be used or not should be used. I would say it depends of the part of the airspace in Europe.
Okay, then there is another question by Jerome Patoureau, and that's thanks for the presentation. Have you scheduled to increase the perimeter of the study then in terms of number of flights, number of weekends, variation due to season, weather constraints, etc.?
Well, we will decide about this in future, but as I mentioned last year, we were presenting a study on the whole FABEC, in which we were concentrated on the seasonal changes. So we looked into summer and winter traffic, etc. So yes, probably we will do that, but depends of the data and depends of the let's say spare time, I would say, because I have to say we didn't do this analysis within any SESAR project. This is a pure research, or let's say enthusiasm of three of us who were working on that. So hopefully we will expand our scope of the study.
Okay, then finally, Milan suggests a nice follow-up to involve the stakeholders. And he isn't asking you to comment. Okay, thank you, Fetja.
Thank you all. Thank you, Henk.
Then we can hand it over to the organizer.
Yes, please.
Okay. Welcome, Tatjana.
Hi, everyone.
So you're going to talk about integrating weather impact in the remote tower control staff scheduling. And Tatjana Polishuk is assistant professor at Linköping University. And she has a very impressive background in studies before starting this. So Tatjana, very welcome to present your investigation in remote tower control.
Thank you. My name is Tatiana Polishuk. I'm an assistant professor from Linköping University, and this work is about integrating weather impact into remote tower center staff scheduling and planning. I want to acknowledge a joint work with LFB and Liu and my colleagues Billy, Anastasia, Christiana, and Valentin, who worked with me on this topic. Understanding the impact of weather on air traffic management is a challenge, and it's recognized by SESAR and Horizon 2020, and it's studied in several SESAR projects. And this work is also a part of SESAR Engage project, integrating weather prediction models into ATM planning. It's also supported from Swedish Transport Administration, Trafikverket, through CAPMOD project. Weather significantly impacts controllers' work. It may result in increased communication with ground and the pilots, and more frequent observations out of the window, and probably changes in arrival and departure procedures and other additional tasks. There are staff planning challenges which are not addressed well in conventional towers. Staff adjustments are quite rare, which means that almost never extra controller is introduced or invited to the tower just because of the bad weather conditions. But in remote towers, the weather impact is to be integrated into automated rostering and planning, mostly because of multiple operation challenges. We need to ensure that no controller is confronted unmanageable workload due to extra tasks at two simultaneously controlled airports. Last year, we did field studies at conventional tower Bromma. We compared subjective and objective measurements, did videotaping, communication duration measurements, and noticed that out of the total communication duration, about 1/4 was due to snow sweeping procedures. We noticed that there are no good measures or classifications for the weather impact on ATCO's work. And in this work, we target to answer the challenging research questions: how different weather phenomena impact ATCO's work and workload at different airports, how to quantify the weather-induced capacity reductions due to extra tasks, and how can we actually integrate this impact into RTC staff planning. This work also contributes to the safety assessment of multiple operation, which is required by unions and regulation bodies. Our strategy consists of the following 7 steps. First, we identify the impactful weather phenomena for each airport in consideration and define thresholds for these impactful weather phenomena based on the interviews with the experts from the towers. When we choose several dates when as many as possible weather phenomena were observed, and calculate the probabilities of the weather phenomena exceeding the threshold values from step 2. And then we also calculate the probability of any impactful weather phenomena to occur per hour at each airport. Take the flight movements data and input all of this information into our optimization framework for optimizing the staff planning at RTC to obtain the distribution of the necessary number of controllers for this assignment. We choose 5 Swedish airports, either operated remotely or planned for remote operation. Airport 1 is a small regional airport with only a few scheduled flights per hour, located inland north of Arctic Circle. Airport 2 is also a small regional airport with regular scheduled flights, open mostly 24/7 with some exceptions. It's located on the east coast and also in the north. Airports 3 and 4 are small regional airports with regular scheduled flights, both in East Coast, and Airport 5 is a medium-sized airport with multiple scheduled flights, open 24/7 in a coastal location in the south of Sweden. Our experts were chosen with a significant operational experience at these towers. 2 of the 3 were male, 1 female, with average age 46, experience at ATCO 17 years, and experience at these towers about 13 years on average. 2 of the 3 actually worked remotely. 1 ATCO answered questionnaires about airports 1, 2, and 3, 1 about 2 airports, and 1 about airport 5. We conducted structured interviews via Zoom. Each lasted about 2-3 hours. First, we asked about the background information on ATCO experience, then common questions about different weather at the airport in consideration. Then we also discussed extra controllers' tasks associated with which weather phenomena, such as snow, low visibility, precipitation, excluding snow, wind and convective weather. We asked how the weather is measured at the airport and also filled in the list of additional tasks extracted from Eurocontrol hazard weather assessment cards associated with minor, moderate, or severe occurrence of each weather phenomenon. Examples of the additional tasks due to different weather conditions are listed here. They include anticipation, condition detection, visual observation, runway closing and opening, early warnings to pilot, arrivals clearing to holding areas, increased frequency, occupancy time, frequent meteo update reports. And then we translated the controller's verbal answers into numerical values. For example, yes was translated into value 1, no 0, and everything in between yes and no are different degrees of uncertainty, like rarely, sometimes, maybe, often. And if it's kind of more than yes or more often than usual, then it's given a value of 1.25. When we sum up the numerical values reflecting controllers' answers and divide them by the total number of additional tasks to obtain these impact tables for each of our snow phenomena on our airports. For example, in snow table, we can see that for the airport 1 located in the north, the impact of moderate intensity of the snow has quite high number, while for the southern airport 5, even severe snow doesn't cause that much of a trouble, which can be explained differently. For example, larger airport 5 may have snow sweeping procedures organized better, and controllers do not experience overload because of that. Or maybe they don't actually observe that much of a snow in the south, while the opposite trend is observed for convective activity. We see that only severe occurrences of convective weather actually impact northern airports, while even light convective activity may result in a high task load for the controllers, which again may be explained by that this weather activity, convective activity, is more often observed in the southern airports. And in order to differentiate between the impact of different weather intensities on different airports, we introduce a threshold value corresponding to at least sometimes or can happen answers of the controllers about the amount of additional tasks. And when we summarize our findings in the table for each airport and for each weather, we have the intensity which should be taken into account for future staff planning. When we translate different intensities of the weather phenomena into numerical values using ATCOS answers, which may be different, for example, for strong winds, severe winds are associated with 25 knots at one airport and 35 at another airport. We also refer to literature and use historical weather database ERA5. And when we choose several dates for consideration, when the weather phenomena were actually observed, these example weather dates were November 13, a winter day when we had 3 out of the 5 weather phenomena at different airports, snow, low visibility and precipitation, and one summer day in July 29th in 2020, a summer day with a low visibility, wind, precipitation and convective weather. We use ensemble prediction systems, EPSs, from the same ERA5 database, which contains 10 ensemble members with 3-hour granularity. And for each airport and weather event which exceeds the threshold, or weather measurement exceeding the threshold, we define an indicator W, which is equal to 1 when some ensemble member J actually indicates that the weather event exceeds the threshold, otherwise it's 0. And for n ensemble members, n is equal to 10 in our case, the probability of some event I to happen during the period H at airport A is defined as a sum of these indicators divided by the number of ensemble members n. Then another indicator I shows that some impactful weather event happens at the airport, and the probability of some impactful weather event is calculated according to this formula in the end. And our assumption here is that different weather events at one airport are actually independent but can happen simultaneously. So first we obtain the table, for example, for November 13, for all our 5 airports. For each hour of this day, we have some probability of each of the 3 observed weather phenomena. as from the database we have observations only per 3-hour periods. We propagate them to the nearest neighboring hours, and for each airport now we have a probability of each weather event to happen during each hour. And when we calculate the probability of some impactful weather, one of the three, to happen at each hour at each airport, and summarize in another table. Looking at the table, we can conclude that for some cells, we should take into account the weather for sure when the value is equal to 1, or we can ignore any weather events when we have zeros. But for all the intermediate values of the probabilities, we need to decide what to do. And what does it actually mean that we have some probability of some impactful weather event at the airport during this hour? Do you remember all good anecdote when the blonde is asked, what are the chances that you meet a dinosaur on the street, and she answers 50%. Why? Well, either I meet him or not, right? So we apply similar strategy here. We either account for the weather at this particular hour at each airport, or we ignore it. Now let's look at some shorter period during this day from 12 to 20, and again we have zeros in some cells and ones in the other cells which stay unchanged, and for all the intermediate values of the probabilities we apply on and off strategy. So each 0 or 1 in each of these cells result in a separate scenario. They can be either 0 or 1 for each of them, and I presented here a couple of scenarios for that. Now let's calculate how many of such scenarios we can have. Let X be an indicator that some impactful weather actually happens during our H at airport A. And scenario X is actually a binary matrix of the size of the number of airports multiplied by the number of hours, which describes the weather situation at all airports. And there are 2 in the power of the size of this matrix of possible scenarios, and the probability of each scenario X is calculated using the formula shown here. And again, our assumption is that weather events at different airports are independent. And as a next step, we analyze flight data from Flight Radar 24 to obtain the number of movements, either departures or arrivals, at each hour at each of the airports. And now we are all set to start calculating the necessary number of controllers to cover all these movements. We use the optimization framework developed by our group for optimization of staff scheduling at RTC, which inputs flight movements at several airports per hour and outputs optimal assignment of controllers to RTC airports per hour. And with respect to the constraints, operational constraints and controller shift constraints, for example, no more than 2 airports can be controlled by 1 ADCO. Now we add a new constraint to force that the airports experiencing impactful weather events during some hour H are operated in single mode during this hour, which means that the controller can put all his attention at each airport with significant impactful weather. We formulate the problem as a mixed integer linear program and solve it using AMPL Gurobi solver on a powerful supercomputer machine at LiU. And the resulting distribution of the optimal number of controllers for November 13 for the given time period looks as follows. When the weather is disregarded from optimization, we need only 5 controllers to cover the operation during these hours. But when we take into account the probability of all the weather events, we need 5 controllers with the probability 87%. But if you want to ensure safe operation in all cases, we would better employ 6 controllers for that. Then we perform similar calculations for July 29th, the summer day in 2020, in which 4 weather events were observed at different airports, from which we derive the probability of some impactful weather events at these airports. We choose another period of time, 9-hour period, and take the flight data movements at all 5 airports during this period. And the resulting distribution of the optimal number of controllers for July 29th looks a bit differently. So again, taking no weather into account, we need only 5 controllers. But if we want to take into account weather, we may employ 6 with high probability or 7 with equally high probability. And sometimes, rarely but still, even 8 controllers are needed, which demonstrates that we cannot disregard weather in this case. In conclusion, we outline that there are no reliable measures or classifications for weather impact on ATCO's work. We propose a strategy as a first step to fill in the gap. We model the probability of impactful weather events using experts' opinions and incorporate it into the staff scheduling framework for RTC. The obtained results and distributions for the example days demonstrate that ignoring weather impact can lead to understaffing or controllers overload. And we want to stress the importance of developing meteo solutions for better staff planning. I want to thank you for your attention. I'll be glad to answer your questions via email or any other communication means. Bye for now.
Thank you, Tatiana.
Hi again.
I will clap again, but I'm the only one.
Thank you.
So now we can go to the questions. I see that you already answered the questions online.
I did my best.
Yeah.
Yes.
But I think it's good that we just go through them. So the first question was from Milan. Could they also used for the weather forecast? Oh no, I'm sorry. I must go up.
It's not the first one, yeah.
Yeah. Do airports already know these probabilities from the past and current practice from local meteo officers?
Yes, and my answer is that they use historical weather data provided by in the form of EPS and this ensemble forecasts. And yes, they're like from the past observations.
Yeah, so that also answers the second question from Milan. And then the third question, Milan, have you tried to link these weather impacts on the controllers and pilots at the same time? Which ones could be more impacted?
So my answer was no, because the purpose of these impact factors were just to staff planning on the ground for controller staff planning, and pilots would definitely come up with another set of impactful factors, another set of task load, different tasks controllers and pilots actually perform, and definitely have different impact on their work.
Yes, that's clear. And then the fourth question is, how far are these airports from each other regarding the assumption that the weather impacts is independent?
Yeah, in general, they are spread out around Sweden, but yes, some of them are quite closely located, and for future work, we are definitely looking at the interdependencies, joint probabilities for the different weather phenomena. It's not an easy thing to take into account, not that many meteorological products available for that, but we are looking forward to improve it.
Okay, then the next question by Milan is, as far as I know, the staff ATC at airports is standardized.
I'm not sure I understand what standardized means.
Maybe I can translate it another kind of question. And now you did analysis how many controllers you need with remote tower setup on multiple airports. But if you didn't have remote tower, then you needed controllers in each airport. How many you would need then for these 5 airports?
Definitely more. We did this comparison in a previous work. So we looked at these same 5 airports. To provide safe operation for the same day movement for some particular month, they needed 17 controllers in 5 airports, while in remote towers, it may be sufficient to have 8 to 10 controllers. So it's definitely about 45% improvement of efficiency when you gather all these airports in remote tower.
Okay, thank you. So Milan, if this answers your question, otherwise just type in a follow-on. I also have a question that has to do with your slide, I think slide number 12, where you have these interesting
I'll share my
heat tables.
Yeah, I will share my slides.
Yeah.
Hope you can see it now.
Yeah, I think one further. It's with the heat. Yes, that one. Yeah. So what I was surprised about is that it looks like that in this heat table, there is a combination of a frequency and the effect, the severity for the tasks. And there I'm a bit surprised. Wouldn't it not be more logical to split them, that you evaluate from the controllers how often does happen severe snow? And if it happens, and of course for airport 5, it happens less often than for airport 1, and how severe it is for task, increasing of task, if it happens. Since now I see one heat indicator for a kind of product of the two. Can you explain? Maybe my interpretation is wrong, that may also be.
No, you're absolutely right. So it's a really good point here. So we asked controllers about their additional tasks when the weather of some intensity happens. We discussed them, what they consider to be light weather phenomena, light intensity of this particular weather phenomena, moderate or severe, and asked what additional tasks they experienced due to this severity. But we did not took into account how often this may happen. So of course, in the southern airport, they don't observe that much of the snow, especially last years. So probably they underestimate their impact. So they just don't see it that much. Same in the north, they don't actually look much at the convective activity because they don't have it that much. So yes, it's a good point, and I don't see right away how to implement both in the same impact, but we'll think about it.
I think it can be done, but then you must go back to the controllers and really split it in 2 questions. They have become very clear that they must make this mental exercise to keep the split.
Yes, it may make sense first to analyze the weather data. Since we have weather data for the whole year, we can look how often each weather happens and probably ask, depending on the proportions of how many days they may have observed this weather, what are their reactions. It's a good idea.
Okay. Okay. Any other questions? I think all the questions have been answered. So thank you very much, Tatjana, for the very interesting research on remote tower controller, which is an impressive concept. Thank you very much.
Yeah, thank you.
So now we can go to the final presentation in a minute. David, you are ready?
Hello, Henk. Yes, I'm ready.
Very welcome.
Thank you.
So, David Mogolfi Gonzalez, he is a data analyst at Nomon. And I must also say you have an impressive background, has been in many European countries working as a professional. And now your focus is on evaluating data-based evaluations of in air transport. And this time you are going to present evaluation using Asian-based modeling and simulation of flight prioritization mechanisms in traffic flow management. So welcome.
Exactly. Thank you, Henk. Thanks for the nice presentation. I will go on by sharing my screen now. Okay, perfect. So yes, as Henk said, I will try to show you during this half an hour the work that we have developed on the evaluation of flight prioritization mechanisms through the ATM-based modeling. This work presented here is framed within the Engage Catalyst funding project named Exploring UDPP Concepts through Computational Behavioral Economics. However, the work that I will present today, it's a little bit more focused in the ATM-based modeling approach, use it for this model for the mechanisms evaluation. I will divide my presentation into 5 different steps. First, I will start with the background and motivations. Then I will talk a little bit about the flight prioritization mechanisms that we have implemented. Then I will go on with the modeling approach that we have followed. Then with the simulation scenarios. And finally, I will okay, now.
Your voice dropped down, David.
Yeah.
Can you go 2 slides back? 1 more back?
Okay, yeah. Right now it's okay, right? Okay, so one of the main motivations behind the project, it's basically the demand capacity problem, which is basically the demand when the demand exceeds the declared capacity of an airspace or an airport sector. And in those cases, the network manager issues an ATFM regulation. This regulation imposes ground delays to the airspace users and redistributes the flow, maintaining the required safety levels. This is very important from the point of view of the airspace users, because these delays comes together with an important cost for the airlines. In fact, this cost is non-linear and depends on several variables, like for instance, maintenance cost, fleet cost, or passenger cost, meaning that the same value of delay can translate in a totally different value of cost depending on the flight. For that reason, the airspace users are demanding more and more flexibility in order to adapt their operation in this kind of situations in order to decrease their associated cost of delay. But at the same time, they cannot get rid of this delay because it's an imposition from the ATFM authorities. So how can these airlines deal with delays to reduce cost? One possibility, of course, is to use the prioritization mechanisms that have been developed in order to provide these airspace users with tools to reorganize their flights and reduce the cost of delay. In that context, the SESAR user driver prioritization process, also known as UDPP, was born. Now I will talk a little bit more about the flight prioritization mechanisms that we have implemented. These are the list of the mechanisms that we have selected for implementation in our model. First, we have a baseline that includes the first plan, first served plus slot swapping. Then the UDPP selective flight protection. Then the UDPP extended selective flight protection. And finally, a slot auction. The baseline is basically the current concept of operation. It has 2 different concepts. The first one is the first plan, first served, which is a principle by which all the flights are sequenced according to their estimated time over the specific sector or airport. It's also known as duration by schedule. And the second step will be the slot swapping, which is basically the exchange between ATFM slots between the flights of the same airlines affected by the same regulation. These 2 concepts, these 2 components are together implemented in the baseline scenario. The second prioritization mechanism that we have developed or implemented is the UDPP selective flight protection. This concept is based on the duration by effort principle, meaning that you have to give something first in order to get a reward. In that context, you have to suspend a flight, absorb some delay, in order to protect another one. This provides extra flexibility for all the airspace users that know in advance the high value of one of their flights, so they can protect it at expense of a less valuable flight. Thanks to the automation, the new sequence of slots will include that request. This UDPP automation is based basically on two steps. First, a simple swap is performed, and in the second stage, the network manager will relocate the protected flight at the first possible slot at schedule, trying to comply with the schedule restrictions, which imposes that a flight cannot depart before its original departure time. The third mechanism is the extended selective flight protection. This concept is very similar to the previous one. In fact, it's considered as an extension or a complementary mechanism. But here, the potential advantage of the mechanism is the ability to provide some flexibility also to airlines with a low number of flights involved in a regulation. For example, airlines that only have one affected flight and therefore cannot carry any type of swap. The operation here is very simple. You only have to suspend a flight by absorbing delay, and in exchange you get some proportional credits that the airline can use in the same hotspot in order to protect a flight, or the airline can save those credits for using in a future hotspot in the same location or in another location of the network. Finally, the last mechanism that we implemented is the slot auctioning. Our implementation of this auction is a primary auction, and basically is the process by which the airlines compete for the slots by offering some bids to the network manager, which at the end will sell the slot to the highest bidder. In this case, we don't have any enforced first plant, first served sequence, but the sequence here is generated directly as a result of the successive auctions of the slots. Again, each slot is auctioned following the restriction imposed by the schedule, as I mentioned it before. Now I will introduce the modeling approach that we have followed in our simulation model. Basically, the model simulates a day of air traffic operations where the network manager takes care for the flow management and the airlines make decisions on how to deal with the delays. The simulation model is based on three main pillars. First, the simulation environment, which includes the network, the flight variables, and the mechanisms. Then we have the agent-based model, which includes the agents and their behavior. And finally, we include the performance framework, which includes several KPIs and metrics that we are using in order to measure the performance of the different mechanisms. The simulation comprises four main stages. In the first stage, the network manager will estimate the future demand for all the network within a given period of time. If the network manager detects an imbalance, it will initiate a regulation. When this regulation is initiated, we can go to the second stage. This is where the network manager will issue all the ATFM slots. Here the delays are calculated. So all the flights involved are delayed. Here we can differentiate two resolution paradigms, the first plant, first served, and the auctions. In the third stage, the airlines develop the decision process. Here they evaluate all the possible options available with the objective of reducing the cost of delay associated with all their affected flights. At the end, the fourth stage, the network manager accepts or rejects this request. Once this process is completed, the delays are definitive and the airspace users can update their flight plans. In order to model this complex system of interactions, we have derived a series of hypotheses or simplification. The most relevant ones are listed below. Flight traffic is checked by the network manager in time windows of 15 minutes and with 2 hours in advance. Then only ground delays are permitted. A flight can't occupy an ATFM slot if this creates a demand capacity problem with the flight in an already resolved time window. The resolution order of the hotspots in the same time window and the order in which airspace users request prioritizations are randomized. And finally, the reroutings are not considered. When we speak about the network, we can distinguish three main parameters. First, the airports. We have included 5 different airports, which are a mix of hubs and secondary airports. Then the sectorization. We have divided our network in 9 en route sectors, plus 1 terminal maneuver area around each airport. At the right, you can also see an illustration of the topology of the network, where we can see the airports, some waypoints, and also the routes between the different OD pairs. Finally, we have the last parameter, which is the aircraft. We have included in our model only 2 aircraft types, 1 narrow body and 1 wide body. Now talking about the flight variables that we have to input in our model, the first one is the flight schedule. And the flight schedule is essential for the network manager in order to estimate the demand. And in our case, it was built based on real flight data extracted from a SO6 file. And then later the data was filtered by 5 selected airports. Later, the airport and sector capacities were scaled to generate the desired demand capacity relation. With all this information, the flights and the flight plans are created. The second flight variable input is the connectivity of the passengers. Here, in order to generate the passenger demand, a passenger file was built based on some relevant assumptions that are listed below. I will comment some of them. For instance, only flag carrier airlines have connections, passengers have a maximum of 1 connection in their journey, or the waiting time for connecting flights lies between 45 and 120 minutes. Now we arrive to the agents. The agents are, in fact, the main component of the agent-based model. Here we only consider 2 types of agents, the airlines and the network manager. The airlines are the main agent of the simulation, and its main functions are computing the cost of delay and making flight prioritization decisions. In our model, we only have included 5 different airlines, which can be classified in 2 groups, which are differentiated according to their network configuration model. For instance, airline 1, 2, and 3 are represented as flag carrier airlines with a hub and spoke network configuration. Airline 4 and 5 are represented as low-cost airlines with a point-to-point network configuration. On the other hand, the network manager is the agent in charge of the ATFM processes. Its functions are detecting the demand capacity imbalances and applying the prioritization mechanisms. Now I will show the different simulation scenarios that we have considered for this work. The main simulation parameters to take into account are the traffic level and the congestion level. However, both parameters are kept constant through all the scenarios tested. The reason for that is at the end, the objective of the work presented here is just a first approach to the measurement of the performance of the different mechanisms rather than a detailed sensitivity study with a large number of combination of parameters. So at the end, we only have 4 different scenarios, which contain a different mechanisms modeled inside. The scenario 1 includes the baseline. The scenario 2 includes the selective flight protection. The scenario 3 includes the extended selective flight protection. And the scenario 4 includes the slot auction. Finally, we arrived to the project results. First of all, the performance assessment framework that we have generated includes the KPIs of punctuality, cost efficiency, and equity. Now we will show all the results by each one of these KPIs. First, the punctuality KPI shows the flight departure delay and the PAX arrival delay for each of the 4 scenarios tested. So we have the baseline, the selective flight protection, the extended selective flight protection on the auction. From these figures, we can derive some conclusions. First of all, the selective flight protection punctuality performance is the worst of all mechanisms. This is something counterintuitive at first sight, because despite of offering more flexibility to the airlines, this type of mechanisms ends up with worse result than the baseline configuration. The reason for that, or the reason that we found for that, is that this extra level of flexibility allowed the airlines to make more optimal requests, which in most cases involved larger alterations in the flight plans, and at the same time involved larger variability of the demand. This variability of the demand caused some downstream network effects that at the end, for some cases, motivated the cancellation of several flights due to missing curfew. On the other hand, the extended selective flight protection mechanism presents a slight improvement compared to the baseline scenario. Finally, the auction scenario provides the best punctuality results. However, it's important to remark here that the auction does not order the flights by the estimated time over, but according to how much the airlines are willing to pay for the slots. At the end, this paradigm ends up with fewer empty slots because this first plan, first served order does not have to be enforced, and consequently, the usability of the network is increased. It will be interesting to analyze in the future if this good performance is only due to this factor or it's due to the inherent nature of the market mechanism. The cost efficiency KPA is measured by the cost of delay per flight. Here, a similar trend to that observed for the punctuality indicators can be observed. The cost of delay of the scenario with the selective flight protection mechanism exceeds the value for the baseline scenario. Additionally, the cost of delay of the scenario with the extended selective flight protection is lower again than the baseline scenario. The reason for that is like here, the extra flexibility allows the airlines to make more optimal decisions and at the same time to efficiently solve the possibly downstream network problems that arise from the demand variability. Finally, the auction-based mechanism presents the best cost-efficient levels. However, it will be again interesting to see if this performance is only due to the factor of the network or to the nature of the market mechanism. Finally, the equity KPI shows two different metrics. Here we have the percentage of change in delay relative to baseline delay and the change in airspace users delay compared with other airspace users delay. Here you can see that the metrics are disaggregated by airline and also that are measured against the baseline scenario, which is considered the best equitable solution. What we can extract from the results here is that the scenario with the selective flight protections shows how all the airlines experiment an increase in the associated delay. But there are two airlines in particular that take the most of this increase, Airline 1 and Airline 3. Talking about the extended selective flight protection mechanisms, it's obvious that it reduces the global delay in the network. However, this global improvement in the delay situation is not distributed in an equal way among all the airlines. In fact, the Airline 1 is negatively affected by the inclusion of the mechanisms, while the Airline 4 obtains a significant benefit. Finally, the auction mechanism displays a more balanced outcome. 3 airlines decrease their associated delay in the same proportion. However, there is still an airline that is harmed by the inclusion of the mechanism. These results are a little bit conditioned by the modeling assumptions and of course require further investigation. However, the following conclusion and future research avenues can be drawn. The added value of the agent-based model has been demonstrated. Some emergent and counterintuitive phenomena which would have been ignored otherwise have been identified for some scenarios. The network effects have a strong influence on the results and therefore are very relevant, so the use of a network model is required. And finally, the result seems to be very sensitive to some modeling assumptions. For instance, the lack of reroutings, some airlines' strategies and behaviors, and so on. So the future research should conduct a more thorough sensitivity analysis to evaluate the response of the model when these factors are modified. So we have arrived to the end of the presentation. Thank you for your attention. If you have any question, I think you have written down some questions, so I will try to answer them right now. Thank you.
Thank you very much, David. You have shown a very nice application of ASIC-based modeling simulation for, you cannot evaluate this in any other way at this moment. I clap for you.
Thank you.
So the next thing is we go to the questions, and I see there are multiple questions from Milan. If others have questions, please enter them. I also see at the end a question by Antonio Franco. I propose, oh, it's just an interesting work. And Laura Vetter, she is asking, auction, does the airline have to bid for a slot even if it originally owned it and is not delayed?
No, I mean, we are only working here with ATFM slots. So if an airline is not delayed, if an airline has some flights that are not affected for the hotspots, they have not the option to participate in this slot. This is only another way to sequence these ATFM slots when several flights get trapped in a congestion area. So the answer is no. And apart from that, very related to this question, we have received some feedback from the airlines, and they told us like they are not really interested in using money for this kind of auction. So another interesting approach for the auction will be to use some kind of virtual currency, for instance, some credits. So we are working now to extend the work towards that direction.
Okay. So let's now go to a list of questions by Milan.
Okay.
So the first is, what about passengers if exchanging slots between own flights?
I'm not sure if I completely understand the question, but the passengers are, when the airlines are taking the decision of changing or prioritizing some flights among other flights, this is happening like 2 hours in advance. So the flight has not departed yet, or it's not even close to departing. So the passengers at these points are in the airports waiting or so on. There are some cases where a flight it's really delayed and it's transporting some connecting passengers, and these connecting passengers obviously missed their connection because of the first delay. In that case, the airline has to relocate those passengers in the next flight. So I don't know.
But I think Milan is meaning here, what is since of course a passenger has a stake at that he gets the right slot and for his flight. So how is that taken into account in your ASIC-based modeling simulation setup? The importance played for the passenger.
All the passengers' costs are included in the cost functions of the airlines. So when the airlines take the decisions, they take into account all the passenger costs. So the cost function includes, as I explained it, several variables. So we included there all the passengers' cost, going from the hard cost and the soft cost. So when the airline is going to take the decision of prioritizing some flight or not, they will take into account this fact.
Okay, thank you. Then the next question is, under what conditions competition for slots is possible? So that is addressing to your framework that you assumed.
Yeah, I imagine that it's related with the auctions, right?
I think.
Yeah, it's what I explained it, like you only get into this, let's say, market, but it of course depends on the mechanism that it's implemented, but you only get into that situation when you have some flights that are affected for this delay. If other airlines have other flights that are not affected by ATFM regulations, they are not participating on this game. Let's call it like that.
So Milan, if this answers your question, if not, you can add another question, follow-up question.
Yes.
Then the next one, it says slot auction applied somewhere and under what conditions?
As far as I know, no, they have not been applied. In fact, this is quite exploratory. What I know is like, yeah, the current concept of operation, it's only limited, well, a little bit now more enhanced, but a limited slot swapping. And also, apart from that, there are several UTPP concepts. I think there are these fleet delay reordering and selective flight protection that are being testing right now in order to, they are a little bit nearer to deployment, but of course there's a lot of investigation going on, and they are trying to be tested in some of their real operation scenarios. But the rest of them, they are quite exploratory. So no, I don't think that auctions have been implemented in these conditions, at least for ATFM slots.
But it may be with your results that people start to think, let's do that, because the alternatives are not so good.
Yeah,
and that was not really known beforehand. Eh?
Yeah, the point here is what I mentioned, that we have in this future research that we are planning to carry out, we have to ensure if these good results for the auction is because of the inherent nature of these market mechanisms, or it's more related with the better usability of the network. We will have to see.
Yeah. And then who is the decision maker at the end, the airlines or ATC? In the concept you evaluated?
In the concept that I evaluated, we have the decisions are taken by the airlines. By the final, let's say, decision is the network manager. But the network manager work only, it's limited, but by ensuring that all the restrictions imposed, for example, schedule restrictions and so on, are being accomplished. So this is the only duty of the network manager. So at the end, the decisions are taken by the airlines. Yes. The network manager is only a regulator, let's say like that.
So then the next question is ATC allowed to apply prioritization of flights? So also in the concepts you studied.
Okay, let me. Here, network manager, it's as I said, it's only the regulator. So then depending on the mechanism that it's included in the simulation in this scenario, the work of the network manager will only be restricted to making sure that the prioritization or the decisions are correct and to apply those decisions. But at the end, is not the agent in that it's taking the decision, is only the regulator.
Okay. And then another one from Milan is, which one would you recommend to airlines and ATC? What are the space for implementation?
I think from the research that we carried out, one interesting maybe the most interesting one could be the extended selective flight protection, the one that includes these credits, because as I explained, it has a really potential advantage that it enables these airlines with a low number of flights involved in the regulations to also take part of this prioritization process, because sometimes some airlines systematically only maybe 1 or 2 flights involved in this kind of unbalanced situations, but they didn't have the opportunity to apply any prioritization because only the swap capability was available. And if they only have 1 flight, this is something impossible. So I think this one, it's quite interesting. And I will also answer the next one here, because we are trying to elaborate this future work, and we are doing so, for example, in the exploratory research project named Beacon. We also have presented here at the seats a poster. So if you want more information about it, you can go, and the video that we did is really excellent. You will get quite informed. And yeah, what we want to do is, of course, to try to include more advanced decision strategies inside the agents, in particular inside the airlines, and also to extend maybe the simulation to other flight prioritization mechanisms.
Okay, and then a question by Antonio Franco. It seems that airlines with smaller aircraft willing to pay less for each flight, so they are in a worse position in auction. Is that true or not?
Let me see. Well, it depends on how do you implement the auction. I mean, the implementation that we did on the auction, that you can find, of course, in the paper, because I didn't include all the details for time reasons. But what we developed is different airlines strategies. So we developed like 3 levels: one conservative, one optimistic, and one neutral. And then we gave this kind of approximation to the different airlines. And at the end, what the airlines are doing is to calculate the bids by thinking of the worst possible position that they could get. And depending on the level of behavior that we implement inside, this worst possible position varies. More information can be found in the paper.
But I think that to find this out, you can set up an Asian-based model scenario where you can explicitly experiment it with a smaller airline with smaller aircraft.
Yeah.
Isn't it? Yeah. Then the question by Mate Selectin: in reality, passenger interest and airline interest might be different. Airlines may be looking for a cost optimization rather than passenger cost optimization. How can you address that in the future work?
Yes, that is true. And well, it at the end, it depends on what we include inside the model. I mean, the good thing about this bottom-up approach is like you can change some things, little things inside the behavior of the agents, and run the simulation and see all these emergent phenomena coming out. Of course, the approach that we took in our work was more related to airlines cost optimization, and we didn't focus on the interest of the passengers. But it's a possibility that you, of course, can include. You can include some strategies inside the airlines agents. For instance, you can say that if they are if they have let's say a large number of connecting passengers for a flight, they always will wait sometimes in order to wait for the passengers that possibly have been delayed in a previous flight. So this kind of strategies can be implemented inside.
Okay. And then from Milan, a question: did you take into account the cost of slots? Look, for example, at Heathrow Airport and think about your strategies that you tried.
Did you take into account the cost of slots? I assume that you are talking about airport slots, right? No, we are not taking into account any cost of airport slots, because I mean the flight is gonna end up departing. I mean the reason of the delay, it's not due to the airline's work, it's due to ATFM problems in the network. So they don't have to be penalized for that. They are not losing any airport slot for that. So we are not going to, we didn't take that into account. But it's good to know. I will check that in case we want to do something similar in the future.
It looks like to me that it is also then a direction for extending your Asia-based model and simulation. And so also study that part.
Yeah, could be. I will study this for sure.
So then there is a question and a remark by Milan. He likes it very much and he is saying, bring it close to reality. So that's a good question. If you look at the opportunities that are there, then you can have one direction thinking, let's first explore more strategies before going closer to reality, or first go now close to reality. Which has your preference at this moment?
My preference, in fact, in this Beacon project that I mentioned, we are going both ways. We are implemented again this kind of simulation. We will, of course, reformulate maybe some of the hypotheses in order to evaluate or to try all these research avenues that I highlighted before. But at the same time, we will use a larger agent-based model. It's called Mercury, and at the University of Westminster are working with this in order to evaluate this in a larger network. I think it will be a real network, the ECAC area. So yeah, the answer will be both directions.
Okay, thank you. Then I also have a question myself, and it has to do with the equity.
Yes.
I noticed that that's a very important result you found, that for some airlines, the net effect is not so good. But the important thing also is that you take as reference what you say, the baseline. And the baseline is as it currently is, I think.
Okay.
But maybe the current baseline is already not equal for all airlines. So the question really is what is your good reference point for equity?
Well, this is a good question. And we, of course, took the baseline as the best possible solution because we received some feedback from Eurocontrol, and they what the system right now is working by the first plant first served. So it's quite, let's say, fair. If you were planned to arrive at this time, if you get delay, it's more convenient. I mean, it's fair that you receive the first slot and the next one will receive the next one. So it's quite fair, and it's understood like that from the point of view of the airlines. And then the only thing that is on top of that is the slot swapping. But the slot swapping, it's a capability that enables you to change your flights between your own slots. So you are not affecting any other airline. So you are not producing any negative impact on other airlines. So that's why we consider that as the most equitable scenario. I don't know if this answers your question.
I will say, if you look from the auction, then certainly you see some airlines are seen they are losing, but be aware that maybe because you take for equity the baseline as a reference point, and that is not per se right. So there is a kind of lack of a proper equity criterion or equity metric.
I mean,
yeah.
We during all the work we were in contact with Eurocontrol. There is a UDPP team that is working on all these prioritization mechanisms, and this is something that was like pretty clear for them that right now what we have is equitable, and everything that we want to build on top of that has to maintain this level of equity. I mean, equity in a sense of fairness, like you are not going to let something in if this is only going to help this airline and not the other one. I don't know if maybe maybe the thing that wasn't clear was the definition of equity that we have. Maybe I should have included there. But if you follow this definition, then instantly you match this definition with the baseline. Yes.
Yeah, that may be that currently it's automatically applied, but it's not necessarily the theoretical correct way. But thank you very much for your presentation and for addressing these interesting questions.
Thank you, Henk.
And that brings us to the end of this session. I thank you all for the excellent session where you showed very interesting results for complex problems. Thank you very much.
Thank you all. Thank you, Henk. Bye-bye.
Thank you.
Bye.
Bye-bye.
Just to remind Chris, do we have a teasers, poster teasers maybe?
The aim of the project is to adapt dynamically dominant flows thanks to the daily demand of the airspace user. This flow will define a network of airstreams similar to corridor or highways. The primary element of an airstream is its backbone, called the airstream reference track. It's a curve defining space. Traffic lanes are then set around the central axis, and on the periphery, integration lanes allow the aircraft to enter or exit. Flight using this structure are distributed on the lanes according to their flight levels and speeds. The collaborative management is then applied based on automated avionics capabilities and aircraft data exchanges. Maneuvers are however permitted within the airstreams, such as overtaking a slower flight. Calculation of complexity maps will allow to evaluate potential benefits of the implementation of airstreams.